Hello guys, to finish up section 1-2, I need to get some vocabulary going with you about minimums and maximums. The difference being whether they're locally or absolute minimum or maximum. This graph will continue as high and as low as it wants because it goes on forever. So this point here is a local maximum. And that coordinate, so you give coordinates. How about negative 1, 1, 2, 3, 4? How about negative 1, 4? Would be locally a maximum. Likewise, this is locally a minimum. So how about we go 3, 1, 2, 3. There aren't any absolute minimums or absolute maximums because there is no absolute limit to how high or how low the graph goes. This one goes on forever as low as it wants, so there is no absolute minimum. This is the maximum height that the graph goes, so that's an absolute max. And that coordinate looks like, how about 3, 10. Okay. This point, locally on the graph, that's a maximum. It's not as absolute high as it goes, but in the local area of this graph, that's a maximum. So we'll call it negative 1, 1, 2, 3, 4. Negative 1, 4. This point, locally, would be a minimum. So 0, negative 2. This graph goes as high as it wants, so there is no absolute maximum. These 2 points are the same depth down, so they both are absolute minimums. 1, 2, 3. We'll go 3, 2 over, 2 back, and down 3. So there are 2 absolute minimums. Minus 2, minus 3, and 2, minus 3. Because it's 2 over, 3 down. Okay. So you can have more than one absolute minimum or maximum. Locally, this would be a maximum, 0, 2, and there's no local minimum. Alright, on this next one, it goes as high as it wants, so there is no absolute maximum, but it does go as low as it wants. And that looks like about 3, negative 10. Locally, that's as high as it goes. And then I have a local minimum, we'll call negative 2, 1, 2, 3, 4. Negative 2, negative 4. Okay. On this one, that would be as absolutely low as it goes. So that would be 0, negative 3. There is no absolute max because it goes as high as it wants, and there are no local because there's only an absolute. Okay. Next page. Piecewise defined functions. Graph them in pieces. Here we got a boundary line, a demarcation line. Oh my goodness. Maybe I should have more caffeine. Maybe that'll help me draw better. Alright. Negative 14 is the y-intercept. So I go all the way down to negative 14. That's negative 13, so there's negative 14. I counted it ahead of time. Up 3 over 1. 1, 2, 3 over 1. 1, 2, 3. 1, 2, 3. And so on. This whole thing, there we go, not so bad, not perfect, that whole thing's the line, but it's only good less than or equal to the boundary. That's the boundary line, that would be less than the boundary, so I need to erase anything that's greater than the boundary because it doesn't belong. Okay. This next one, the y-intercept is 6. 1, 2, 3, 4, 5, 6. Slope is negative 2. Oh, let me go back. This one had a closed circle because it has the equal sign. This one turns out it's going to hit at the same point But because this says strictly greater than the boundary, at the boundary it's an open circle. But previously I had put a closed circle there, so you really can't tell the thing is an open circle because there's a closed circle sitting there. So there's your final answer. Now, in this problem, they happen to intersect at the same place in the boundary. They don't have to. Say this is an open circle, and the line runs off there. You could have another line, say, is here at the boundary and runs that way. Or if this is the boundary, you could have a line, closed circle, heading down that way. And on the other side of the boundary, you could have one that, I don't know, we'll go down here. Open circle here, heading up. Okay? Or open circle there, heading down. It doesn't really matter. The point being, they don't have to intersect at the boundary. Okay? They don't have to. It just so happens this one did. All right. Here we got a boundary at -2. You could graph y is equal to negative x plus 1 squared plus 0. And you guys know from doing the translation form, its vertex is -1, 0. So it's this graph pushed 1 unit left, and then it's upside down. 1 unit left, upside down. It's the same graph as y is equal to x squared. So to show you how to do it quickly, if I put a 1 in, I get a 1. If I put a 2 in, I get a 4. I put a 3 in, I get a 9. So to help you draw it, you know this is the vertex, -1, 0. If I go over 1, I'm going to go down 1. Over 1, down 1. If I go over 2, I'm going to go down 4. Over 2, 1, 2, 3, 4. If I go over 3, I go down 9. 5, 6, 7, 8, 9. And this thing's going to be symmetric about the vertex. So this whole thing is the parabola. Okay. But it says it's only good greater than the boundary. So greater than the boundary is the right side. So this left side has to come off. And at the boundary, there's an open circle. Okay? Now I need to graph the other one. Y is equal to x plus 3 squared. If you want plus 0, so the vertex is -3, 0. And again, it's a translation of y is equal to x squared, so it follows the same pattern as the previous one. So -3, 0. It's opening up because a is positive. So I go over 1, up 1, over 2, up 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it's symmetric. Oops. So you guys for the interruption. All right. So then I made a mistake, so that was that point, and then over 1 more and up to that point. So this would be your whole parabola. Again, sorry, I'm consistently missing it. But it says it's only good less than or equal to the boundary. So anything that's greater than the boundary is removed, and at the boundary, because it has an equal sign, it's a closed circle. So that would be your graph, and technically the boundary line isn't there either. So technically you should go back and remove it, but you know, I'm not that much of a purist. That point was a mistake. Okay, so that would be your final answer. All right, you guys have been looking at the tables of graphs to see whether a function is even or odd. The definition of an even function. And remember, these are y values. That let's remember f of x is the same thing as a y value. This is just indicating when you change the sign on the x value that you're inputting into the problem, your y value is remaining the same. F of x means y. F of x means y. In this case, f of negative x. And all that's indicating is you change signs. Like you put in a negative 3 or you put in a 3, you're getting the same y value. So that's indicating that this thing is an even function. An odd function, when you change the sign on the x, you change the sign on the y value. Okay? You change the sign on the y value. Put in a negative 3, you're going to get a y value. You put in a positive 3, the answers differ by a sign in the y value. It means they're the same number. Like, say you got 12, this one's going to be negative 12. Or if that one was negative 12 you got for an answer, this one's going to be positive 12. So this function was even, this function, whoops, is odd. Okay, I have 2 examples there, but I think it's better if I just move over. Algebraically, how to show if these things are even and odd. Well, you could pick a number and stick it in, like f of 2. And you'd have 2 squared plus 7, so that'd be 4, you get 11. Then you could pick negative 2, and you get negative 2 squared plus 7. That's 4 plus 7, oops, is 11. So it looks like the thing is even, because you get the same answer. But that's not proving it. And I hate to use that nasty P word, but prove it. To prove it, here's the original function. Stick in the opposite of x into the equation and look and see what happens. This turns into x squared plus 7. Isn't that identical to what you started with? Yep. So that means the thing is an even function. It's saying that f of negative x, or opposite of x, is exactly the same thing as f of x. So this is an even function. This one, stick in the opposite of x to the 4th, minus 16, opposite of x squared, plus 2. That's going to be x to the 4th, minus 16, that's x squared, plus 2. This is identical. So f of the opposite of x is exactly the same as f of x. So once again, this thing is an even function. This one, f of the opposite of x, so that would be the opposite of x squared plus, whoops, I forgot the 3, plus 3 times the opposite of x, so I ran out of room, minus 2. So f of the opposite of x is equal to x squared minus 3x minus 2. Now how does this compare to the original? Well, first, are they identical? No. So it's not even. Okay? Now, if it was an odd function, and remember, odd is if I change the sign on the input, I have to multiply the original function all by negative 1. That's what that's saying, is that the original function is opposite in sign. So if it was odd, I would expect negative x squared minus 3x plus 2. That would be the opposite of f of x. The definition, once again, guys, is when you change the sign on the x, you change the sign on the function. Changing the sign on the function is like multiplying the whole function by negative 1. Okay? How is this the red? Did all the signs change? No. So it's not odd either. Okay? So that means the graph or the function is neither. It's neither even nor odd. Okay? So let's try this one. F, the opposite of x, is equal to the opposite of x cubed minus 4 opposite of x. So that's negative x cubed plus 4x. How does this compare to the original? all the signs are changed. So this is an odd function because opposite of x generated the opposite sign on the function. So like -1 times f of x. -1 times that would give you -x cubed plus 4x. So this is an odd function. Okay, and that's the end of it. So away you go.